Yes, it was interesting to come up with a heading for this next bit. So there's the heading. Integral of f dash x times function x to the power of n dx. What on earth does it mean? Integration's the reverse of differentiation, as we know. And you'll remember we have a chain rule when we differentiate, which says we bring down the power, lower the power, times diff the inside. So if we see an integral where it's already got some function to the power times the derivative of the inside, then we can go back to the original function and it's simply add 1 to the power over the power. Because if I was to differentiate this function x to the power of n plus 1 over n plus 1, what would I do? I'd lower the power, n plus 1, which would cancel with the n plus 1 on the bottom. Take 1 off, n plus 1 becomes n, and then I would go times the diff of the inside. And so if you notice that pattern, you can save yourself a little bit of time. Now, sometimes they ask questions this way, where they're sort of giving you a really huge hint about it. They'll say, hey, go and differentiate this particular function. In this case, the square root of 1 minus x cubed. So we differentiate it, bring down the power, lower the power, dip the inside, and there you go. I end up with minus 3x squared over 2 root 1 minus x cubed. And then they follow it up with a question which says, go and integrate this. Integrate x squared on the square root of 1 minus x cubed. Now, have a look at the answer we just got when we differentiated. It's very similar to what they're asking me to integrate. The only difference is the constant. So I can create that constant, but of course I can't change the question. So I've created what I got as my answer in the first part, minus 3 on 2, but then to balance it back out the front, I times it by minus 2 on 3. And so it still is the same thing. But I know what I get when I integrate this. It must have been what I differentiated in the first part, which was the square root of 1 minus x cubed. So sometimes they'll ask a question like that. So it's like this huge hint. Go and differentiate this, and then there's a follow-up question. Oh, go and integrate this, and what do you know? They look very similar. But it might not be that obvious. It might be written like this. Just go and integrate x squared root of 2 plus x squared. If you have a look at the function inside the grouping symbol, and in this case the square root sign is the grouping symbol. If I was to differentiate 2 plus x squared, I would get 2x. So that grouping symbol is times, well, not exactly the derivative, but some multiple of the derivative. But I can create the derivative. So 2 plus x squared, what I'd like to see there is not x, but I'd like to see 2x. So I'll make it 2x. But to balance it out, I'll times it by a half. And so now it's in the form of derivative, some function to the power of n. In this case, n is a half. And so I can simply add 1 to the power, 3 on 2, over the power, 2/3. And a little bit of cancelling there, and I get my answer. So that's the pattern we're looking for. Derivative times some function to the power of n. Of course, another way I could do this is what's called integration by substitution. Don't worry too much about this. We'll look at it in a lot more detail next year. But to give you a bit of a taste of integration by substitution, we look at it and say, oh, look, what's causing me the problem is the 2 plus x squared, because I can't expand the square root of 2 plus x squared. So I change the pronumeral. And I say, well, let u equal what's causing me the problem. 2 plus x squared is causing me the problem. So that's u. And if I differentiate, I get 2x. And I just rewrite that and say, well, du is 2x dx. And then I substitute back in. So I change the pronumeral from x to u. So the 2 plus x squared, well, that's u. And the x dx, well, that's half of du. And so I could rewrite this as half times the integral of u to the power of a half. And that's a very simple thing to integrate, u to the power of a half. Add 1 to the power over the power. The 2's cancel, but then, of course, I substitute back in for u, and I get the same answer. As I say, that technique we'll look at in a lot more detail next year. All right, here's a definite integral But again, I've got some function to the power. In this case, the power of, well, it would be negative 3 if I wrote it in indices. So that's what's causing me the problem. Wow, what I'd really like then is it to be times the derivative of x cubed minus 2. The derivative of x cubed minus 2 is... Yeah, it wasn't a trick question. It's 3x squared. We don't have 3x squared. I've got x squared. But that's okay. It's just a multiple. So I'll make it 3x squared, but to balance it out, I'll put a third out the front. And now I have the derivative times the function to the power of n. In this case, that power is negative 3. Add 1 to the power over the power, and we get minus a 6, x cubed minus 2 to the power of negative 2. Sub in 1, sub in 0. There's my answer, minus an eighth. If I'd chosen to do this one by substitution, I would have said, what's causing me the problem? X cubed minus 2 to the power of negative 3. How do you expand out negative 3? Well, I can't. That's what's causing me the problem. So I'll let u equal x cubed minus 2. So du will end up being 3x squared dx. Now, these limits I'm going to have to change in this case because those limits refer to x. Well, if I'm changing the pronumeral, I need to work out new limits. But I've got a formula that allows me to do that. U is x cubed minus 2. So when x is 0, substituting in, we'll get u is negative 2. And when x is 1, u will become negative 1. So my new integral goes from minus 2 to minus 1, and it will just be a third of u to the minus 3. Add 1 to the power over the power. In this case, I don't have to substitute the x back in, because I can just put these limits straight in. And there's the same answer, minus an eighth. So 11h is all about that pattern, finding derivative times some function to the power of n and making use of that pattern when we integrate